The length of a step. Before the story begins, let the body come to rest. Settle into whatever surface is holding you, and let it take all of your weight. There is nothing to do now except grow heavier. Start at the feet. Let the feet go slack, the toes uncurl, the ankles loosen. Let the weight of the lower legs rest fully down, so that nothing in the calves is doing any work at all. Let the knees soften. Let the thighs give up their shape and spread a little. Allow the hips to open and settle, so that the lower back lengthens without effort. Let the belly rise and fall on its own. Nothing here needs holding. Let the ribs move easily. Let the chest be soft and wide. Let the shoulders drop away from the ears. Let the upper arms grow heavy, then the elbows, then the forearms, then the wrists. Let the hands lie open, the fingers uncurled, the palms doing nothing. Let the throat be soft. Let the cheeks be heavy. Let the tongue rest low in the mouth. Let the jaw unclench, so that the lower teeth drift away from the upper teeth. Let the space between the eyebrows smooth out. Let the scalp loosen at the crown and behind the ears. Let the eyes be still behind their lids. Let the forehead be wide and quiet. Now let the whole body be one weight, sinking, with the breath moving through it slowly and requiring nothing. And from here, a story about a shadow and a number and the length of a step. There is a racetrack at Olympia in the western Peloponnese in southern Greece, cut into the earth beside the sanctuary of Zeus. Its stone starting sills survive, and when they were measured, the distance from one end to the other came out at 192.27 meters. Delphi's track, high on the slope above the Temple of Apollo, measures 177.5 meters. Epidaurus comes in at 181.3, Nemea at about 178, and the track at Pergamon, over in Asia Minor, runs to 210. All of these tracks are called by the same word. Each of them is a stadion, which is also the word that comes into English, through Latin, as the stade. In Greek, the word meant both the race and the length of the course, and the length of the course was defined the same way everywhere. 600 feet from the starting line to the far end. 600 feet in a world where the foot was whatever the foot was in the place where you were standing. Tracks that survive vary from about 177 meters to about 210. That is a spread of nearly a fifth. 2 men could each run a stadion on the same afternoon in different cities, one of them covering 30 meters more than the other. Neither of them would be running the wrong distance. The most famous measurement in ancient science produced its answer in stades, and nobody knows how long a stade was. As it is usually told, Eratosthenes of Syene, chief librarian of the Great Library at Alexandria on the Egyptian coast, in the 3rd century before the Common Era, learned that at the town of Syene, far up the Nile at the site of modern Aswan, the sun stood directly overhead at noon on the day of the summer solstice, so that a vertical pole cast no shadow and the light reached the bottom of a deep well. At Alexandria on the same day, a vertical pole did cast a shadow, and the angle of the sun away from the vertical worked out to 1/50th of a full circle. If the 2 cities lay on the same north-south line, and if the sun's rays arrived parallel, then the arc between them had to be 1/50th of the Earth's circumference. Between them lay 5,000 stades. 50 times 5,000 is 250,000. And that, converted into modern units, comes out within a % or 2 of the true figure. Almost every element of that account is either uncertain, disputed, or absent from the ancient record altogether. Eratosthenes wrote a book about the measurement. Its title is preserved, On the Measurement of the Earth. That title survives because Heron, a working engineer at Alexandria 3 or 4 centuries later, quoted it in a technical manual about surveying instruments, saying that Eratosthenes had worked more accurately than others, and had shown in that book that the circumference was 252,000 stades. That is essentially all that is left of it. The book itself is gone. So is Eratosthenes' 3-volume geography. It went out of circulation early. By the 1st century of the Common Era, it was already rare, and Ptolemy the astronomer, writing his own geography in the 2nd century of the Common Era, seems never to have read it. Ptolemy the astronomer is no relation to the Greek kings of Egypt, who had the same name. What survives of Eratosthenes survives almost entirely inside Strabo, a geographer writing under the first Roman emperors, who quotes him at length in order to argue with him. For the actual procedure, for the shadow and the angle and the arithmetic, there is exactly one surviving ancient account. It sits in a book called The Heavens, by a teacher of Stoic philosophy named Cleomedes. Cleomedes is a difficult witness, beginning with when he lived. His book mentions Posidonius, who died around the middle of the 1st century before the Common Era, so it cannot be earlier than that. Beyond that, the evidence is thin and contested. Otto Neugebauer, a historian of astronomy, built an argument from a passage where Cleomedes places the stars Aldebaran and Antares at 15 degrees of their respective zodiac signs. Ptolemy's star catalogue, compiled in the 2nd century, puts them at 12 2/3. Stellar longitudes creep upward over the centuries, so a gap of 2 1/3 degrees, at the rate of drift Ptolemy himself used, is a little over 2 centuries after him. Neugebauer settled on the year 371, give or take 50 years, and the Oxford Classical Dictionary still follows him, dating Cleomedes to around 360 and calling his account of the measurement mostly fictitious. Alan Bowen and Robert Todd, who produced the standard English translation in 2004, reject that reading. That passage, they argue, does not support the inference. The phenomenon Cleomedes describes could not have been observed as stated in any case, since the two stars sit at different heights in the sky, and the bending of light near the horizon spoils the geometry. Their own dating rests on the character of the arguments. Cleomedes attacks rival philosophical schools in a manner typical of the 1st and 2nd centuries and unparalleled after the early 3rd. They propose a range from 50 before the Common Era to 250 after it, with a working guess of around the year 200. The one detailed account of the measurement was therefore written somewhere between 2 and 6 centuries after it, by an author whose date is disputed by 400 years. Cleomedes was not an astronomer either. The Heavens is not a scientific treatise, but a set of lectures, or the written residue of lectures, in which astronomical material is presented in service of Stoic cosmology. Bowen and Todd describe it as ancillary material inside a larger exposition of Stoicism, and they point to the vocabulary of the classrooms scattered through it. Introduction, lecture courses, instruction, learning. Cleomedes sets out a list of things to be assumed. First, that Syene and Alexandria lie on the same meridian, meaning the same line of longitude, so that one is due south of the other. Second, that the distance between the cities is 5,000 stades. Third, that the rays sent down from different parts of the sun to different parts of the earth are parallel, as the geometers assume. Fourth, that straight lines falling on parallel lines make the alternate angles equal. Fifth, that arcs standing on equal angles are similar, having the same ratio to their own circles. Then the observation. At Syene at midday at the summer solstice, the gnomons, the upright pointers of the sundials, cast no shadow. At Alexandria at the same moment, the pointer of a hemispherical bowl sundial, a scaff, casts a shadow that marks off an arc. That arc is a 50th of its own circle. Therefore, the distance from Syene to Alexandria is a 50th of the great circle of the earth. And since that distance is 5,000 stades, the whole circle comes to 25 myriads, which is 250,000. Cleomedes has gnomons at Syene and a bowl at Alexandria, with no well anywhere in the account. The well is in the ancient sources, but it belongs to other authors, and it is not attached to Eratosthenes. Pliny the Elder, in the second book of his natural history, reports that at the town of Syene, 5,000 stades south of Alexandria, no shadow is cast at noon at midsummer, and that in a well made for the sake of testing this the light reaches the bottom, showing that the sun stands vertically above the place. Eratosthenes is not mentioned. Strabo, in his 17th book, mentions the well that marks the summer tropic at Syene, the tropic being the line of latitude furthest north at which the sun ever stands directly overhead, and explains that since people stand perpendicular to the earth and wells are dug perpendicular to the surface, the sun overhead must throw its light to the water however deep the shaft. Eratosthenes goes unmentioned there too. Peter Gainsford, a classicist who has written at length about the sources, puts the position flatly. No ancient source at all anywhere connects that well to Eratosthenes. Reviewers of the standard modern edition of the fragments note that popular accounts nonetheless keep Eratosthenes personally at the wellhead. The scene, a scholar leaning over a shaft of water at noon and seeing the sun's disk reflected back with no rim of shadow, comes to most people from the first episode of Carl Sagan's Cosmos in 1980, which drew on a much older tradition. Cleomedes says the observation was made at the summer solstice. Vitruvius, the Roman architect, writing in Latin in the 1st century before the Common Era, says it was done from shadows measured at the equinox rather than the solstice, and gives the result as 252,000 stades. Marcianus K. Pella, writing several centuries later, also says equinoctial, and adds a detail found in no other source: that Eratosthenes took his number of stades from Syene south to Merae, rather than from Alexandria down to Syene, and that he got it from the royal surveyors of the Egyptian king Ptolemy. The figures disagree as well. Cleomedes gives 250,000. Nearly everyone else, from Pliny onward through half a dozen later compilers, gives 252,000. Pliny calls it an audacious venture, achieved by such subtle reasoning that one is ashamed to be skeptical. Vitruvius, a few lines after quoting the figure, records that there are some who deny that Eratosthenes could have obtained a true measure of the earth at all. A standard answer to the 2,000 stade gap points to arithmetic convenience. 252,000 divides by 60 to give exactly 4,200. Eratosthenes worked with a circle divided into 60ths. 250,000 divides by 60 to give a number with a remainder. On that reading, the calculation produced 250,000, and Eratosthenes nudged it upward to something he could handle. A variant of that answer is that 252,000 divided by 360 gives exactly 700 stades to the degree. That may be an anachronism. A circle of 360 degrees is not attested in surviving Greek mathematics until 2 generations after Eratosthenes, and Strabo reports Eratosthenes' figures in 60ths rather than degrees. It remains the standard explanation all the same, and specialists still routinely credit Eratosthenes with 700 stades to the degree. Christian Carman and James Evans argued in 2015 that the two numbers are not one figure revised but two bounds on the same quantity. If the sun is assumed infinitely distant, its rays arrive strictly parallel, and the calculation gives one answer. If the sun is at a finite distance that Eratosthenes is elsewhere reported to have used, the rays are very slightly divergent, so the calculation gives a slightly larger answer. 250,000 and 252,000 would then be a lower and an upper bracket around a quantity Eratosthenes knew he could not pin exactly. Irina Tupikova has argued instead for two different methods, an astronomical one behind the smaller number and a geographical one, using equinoctial shadow ratios behind the larger. Strabo says where the 5,000 stades came from. Discussing the meridian through Syene, he writes that it runs approximately along the course of the Nile from Meroe to Alexandria, that this distance is about 10,000 stades, and that Syene must lie in the center of that distance, so that each half, Meroe up to Syene and Syene down to Alexandria, comes to 5,000 stades. 5,000 is arrived at by having around 10,000, and assuming that Syene sits at the midpoint. Syene is also about 3 degrees east of Alexandria, so the line being halved is not a meridian at all. The 5,000 is not an independently surveyed baseline. It is one round number divided in two. Eratosthenes' other Nile figures are all rounded to the nearest 100 stades, and several of them to the nearest 1,000. Eratosthenes gives 5,300 stades from Syene to the sea along the Nile, and 5,000 along the meridian. And one reading of the pair is that the smaller figure is the larger one rounded down after allowing for the river's bends. In the one passage where Strabo lets him speak about his own method, Eratosthenes says that he records the distances that have been handed down, but does not validate them, reporting them as they have been received, though at times adding the phrase, by means of a more or less straight line. Duane Roller, whose 2010 edition of the Fragments is the first complete modern collection since 1880, points out that beyond a limited personal knowledge of Egypt, Eratosthenes records only 2 places he had visited, the site of Helike in Achaea and the island of Rhodes. He worked in the largest book collection in the world and had no interest in fieldwork. Most of his distances come not from astronomical calculations, but from itineraries and travelers' reports. A long tradition has nonetheless imagined how the 5,000 stades might have been paced out. Most popular are the Bamatistae, the Macedonian pace measurers who had walked out the distances of Alexander's march, and whose figures Eratosthenes demonstrably did use, though for Asia rather than Egypt. Others have proposed the annual Egyptian land survey, called by Strabo the origin of the science of land measuring, or the sailing time of boats on the Nile, or camel caravans reckoned at 50 days of 100 stades. Camels did not become the dominant pack animal in Egypt until the Roman period, though Ptolemaic desert caravans between the Nile and the Red Sea already used them. The likelier account is that Eratosthenes had access to books, and the books available to him were written by Ptolemaic explorers, admirals and diplomats who had gone up the Nile and come back with distances. Nathan Sidali has argued in detail that the procedure Cleomedes describes is not the procedure Eratosthenes performed. Cleomedes says that Eratosthenes' method was geometrical and was thought to involve something rather obscure, and then goes on to describe a configuration of such striking simplicity that the description undercuts the introduction. There is no enunciation of a result to be proved, no lettered diagram, no geometrical construction, no mathematical argument of any kind. Cleomedes claims all 5 things to be assumed as his own assumptions, and 2 of them, the alternate angles and the similar arcs, are propositions that any Greek mathematician would have used silently. Sidali concludes that Cleomedes rearranged the material to make his own philosophical point about how conclusions follow from premises, and that it is difficult to reconstruct Eratosthenes' approach directly from his account. The one sentence of Heron that preserves the title is also an external check. Eratosthenes, he says, worked more accurately than others. Sidali's point is that Heron, a working technician, would not have been impressed by anything as trivial as the configuration Cleomedes describes. Whatever on the measurement of the earth contained, it was more likely a real piece of mathematics in the manner of Archimedes, with bounds and constructions, of which the shadow and the fraction were a small part. A stronger version of the case holds that Eratosthenes made no direct measurements at all, and that the whole scene with the bowl is a reconstruction after the fact. What Eratosthenes got depends entirely on how long a stade was, and the length of the stade is the part of the problem that has never been solved. 157.5 meters is the number that makes Eratosthenes famous. Multiply 252,000 by that, and you get 39,690 kilometers, against a true meridian circumference of 40,008. That is an error of 0.8%, and the popular retellings rest on that arithmetic. 157.5 comes from no Greek text. No ancient author names a stade of that length. It is a modern back derivation. An Egyptian sconus was 12,000 royal cubits. Pliny reports 40 stades to the sconus. So a stade is 300 royal cubits, and 300 times a royal cubit of 0.525 meters is 157.5 exactly. Put another way, the foot of that stade is half a royal cubit, 26.25 centimeters. Credit for the derivation usually goes to Friedrich Hultsch, whose Greek and Roman metrology of 1882 canonized it, though French scholars had worked out the Egyptian sconus identification decades before him. From Hultsch it passed into the handbooks and into every account of the measurement written since. One genuinely independent piece of evidence supports a foot of 26.25 centimeters. Herodotus describes the tunnel driven through the mountain on the island of Samos in the 6th century, before the Common Era, as 8 feet high and 8 feet wide, with a water channel 3 feet across. That tunnel exists, and excavation measured it at 2.1 meters by 2.1 meters, with a channel 0.8 of a meter wide. 2.1 divided by 8 is 0.2625. That gives a Samian foot of exactly that length, half of a Samian cubit, which Herodotus himself says is equal to the Egyptian cubit. 600 such feet make a stade of 157.5 meters. The excavator who took the measurement weighed a Samian foot of about 35 centimeters against an Attic foot of about 29.5, and preferred the Attic, so even that evidence is contested. A building foot and a travel distance need not be measured in the same unit in any case. Donald Engels in 1985 and Dmitry Shcheglov in 2018 argued that the geographers used the ordinary stade of about 185 meters, an eighth of a Roman mile of about 1,480 meters. 252,000 of those come to 46,620 kilometers, an earth about a sixth too big. That is the kind of error one would expect from round numbers and travelers' reports. Shcheglov's version of the argument is statistical. Take the distances Eratosthenes and Strabo give between places that can still be identified, compare them with the true distances, and work backwards to the stade length that would make each one come out right. Do this for a few hundred routes, and the answer comes out around 150 meters, which looks like support for the short stade. But ancient routes were not straight lines. Calibrated on Roman roads, where the unit is securely known, ancient distances overstate straight-line distances by 25 to 30% on average. That correction applied to 150 puts you back at 185 to 195. If the short stade was deduced from a tacit assumption that ancient distance measurements were highly accurate, it is unsurprising that, substituted back into Eratosthenes' calculation, it makes his result amazingly accurate too. 5,000 stades at 157.5 meters is 787.5 kilometers. A true meridian arc from Alexandria to Aswan is 788. Agreement holds to 0.06%. It also requires that travelers going up the Nile reported to Eratosthenes a straight-line projection onto a meridian that they had no means whatever of computing, over a river route that actually runs more than 1,000 kilometers. Irina Tupikova answered in 2022, in the Archive for History of Exact Sciences, that the whole dispute is a category error. There are two different kinds of stade, whose conflation is what makes the evidence look contradictory. A measured stade is a defined unit, tied to a standard foot, used in architecture and in the laying out of racetracks. An itinerary stade is a distance estimated by travel, reckoned at 240 paces. 240 paces belong to a body. Tupikova assembles the evidence for how long a pace actually is. Carsten Niebuhr, on the Danish expedition to Arabia in the 1760s, counted his own paces and recorded 1,580 double steps per half hour in the heat of the day, and 1,620 in cooler hours. At plausible caravan speeds, each single step comes out between 54 and 66 centimeters, and 240 of those make a stade of between 130 and 158 meters. A traveler in Africa, a century later, recorded steps between 60 and 70 centimeters. Body measurements give the same range. The human foot runs about 15.5% of a person's height, so 600 feet belonging to a man of 1.62 meters comes to about 150 meters, and 600 belonging to a man of 1.72 meters to about 159. She concludes that the itinerary stade averaged somewhere around 150 to 160 meters, sometimes less in bad conditions, and that a stade of 185 meters could not have been paced at all. 240 steps to that length means a step of 77 centimeters, sustained mile after mile, longer than any of the recorded travelers managed. She also turns the statistical argument back on S.H. Cheglov. Weighting the mean by route length, she argues, assumes long routes were measured more reliably, when anyone would expect the opposite. His data are heterogeneous. On her reading, mixing paced distances with geometric corrections and Roman recalculations as though they came from one population. Disaggregate them, she says, and there are clusters near 125, near 160, near 187, rather than one central value. Tupikova's other objection concerns the one archaeological site everyone cites for the 185-meter stade, the Panathenaic Stadium at Athens. That track was laid out in the 4th century, before the Common Era. It was rebuilt entirely by Herodes Atticus in the year 144 of the Common Era, excavated by Ernst Ziller in 1869 and 70, and rebuilt again on Herodes Atticus' plan for the Olympics of 1896. Ziller himself said the original length could not be restored, and gave only a total horizontal extent of 204 meters. Estimates made at the time ran from 177.6 meters for the track itself up to 189.6 for a longer span. 185 entered the literature and has been repeated since. The 185-meter figure, if correct, is correct about a Roman era rebuild by a Roman era builder, and Tupikova suggests he chose it because a Roman mile divides neatly by 8. Nothing about this debate has converged. Its most recent word, published in the same journal in December of 2024, comes from Claudio Narduzzi, an engineer at Padua, who rejects what he regards as a vague itinerary unit. Narduzzi argues from Greek road markers of the centuries after Alexander that main roads were measured as well as the technology allowed, with geographical distances referring to real metrological systems. He answers with 2 lengths, and neither is among the stades already under dispute. 177 meters from the Attic foot and 210 meters from the Philteric foot used in Ionia and on Samos, which is to say, near enough, the track at Delphi and the track at Pergamon. Apparent inconsistencies in the texts on his reading are conversions between the two. Alexandria sits at 31.2 degrees north. Aswan, which stands where Syene stood, sits at 24.09. Their difference of 7.11 degrees is 1 part in 50.6 of a full circle. Eratosthenes 1/50th corresponds to 7.2. His angle is off by about 1.25%. A straight line between the two cities runs 843 kilometers against that meridian arc of 788, and the river route between them is longer still. So if the 5,000 stades reflected how far people actually went, the figure is at least 7% too large for the arc it was supposed to represent. An error in that direction pushes the answer for the Earth's circumference upward. Syene is not on the tropic either. The tilt of the Earth's axis, which drifts slowly over thousands of years, stood in the 3rd century before the Common Era at about 23.72 degrees, and Syene sits at 24.09, roughly 40 kilometers north of the line where the sun stands truly overhead. Sunlight at Syene at noon on the solstice arrived about 1/3 of a degree off vertical. That makes the shadow angle measured at Alexandria slightly too large for the arc it is standing in for, and a larger angle divides into the circle fewer times, so the answer comes out low. The two errors do partly cancel. They do not cancel anywhere near enough to produce agreement within 1%. Getting to 1% requires the short stade, and part of the case for the short stade is circular in exactly the way S.H. Cheglov describes. Not all of it is. The tunnel foot at Samos, and the pacing arguments assume nothing about Eratosthenes at all. Posidonius, a Stoic philosopher who worked on roads a century and a half after Eratosthenes, used the star Canopus rather than the sun. At Rhodes, Canopus grazes the horizon and never properly rises. At Alexandria, further south, it climbs to what Posidonius took to be 7.5 degrees, a 48th of a circle, taking the distance from Rhodes to Alexandria as 5,000 stades. 48 times 5,000 gives 240,000. Strabo reports a variant using a distance of 3,750 stades, giving 180,000. Both figures rest on a bad measurement. Rhodes and Alexandria differ by about 5 degrees of latitude, not 7.5, and a star sitting on the horizon is exactly where the bending of light through the atmosphere does the most damage to its apparent height. But it was the smaller of the two derived figures, 180,000 stades, that Ptolemy adopted, following an earlier geographer named Marinus of Tyre, as 500 stades to the degree, 180,000 divided by 360. Ptolemy took the figure as the generally agreed measurement, and it became the standard value for 1,400 years. Tupikova and Klaus Jews showed in 2013 what that choice did to the map. Ptolemy's source material was distances, and to place a city, he had to convert a distance into an angle using the size of the Earth. Using a circumference of 180,000 stades instead of 252,000 inflates every derived angle by the ratio of the two, 1.4. Latitudes largely survived, because latitude can be got astronomically from the sun or the pole. Longitudes could not be got astronomically in antiquity, so they came from distances, and they all stretched by a factor of about 1.4. The inhabited world on Ptolemy's map therefore spans 180 degrees of longitude when the true span, from the Atlantic to China, is closer to 130. They ran the process backwards. Take Ptolemy's coordinates, recover the distances he must have started from, then reproject those distances onto the larger Earth. The longitude of Athens moves from Ptolemy's 52.75 degrees, counted from his own starting meridian out in the Atlantic, to 23.2 degrees east, against a true value of 23.7. Carthage, which Ptolemy places some 4 degrees too far south, comes back to within about 2 degrees of its true latitude. A regression over 80 towns shows that shifting the origin, and then dividing by about 1.4 recovers true longitudes almost exactly. One assumption about the size of the Earth, propagated through every conversion, bent the map of the world, and the small Earth had a long afterlife. Ptolemy's 500 stades to the degree passed into the Arabic tradition, where the 9th century astronomer Alfarghani gave the degree as 56 2/3 miles. That figure is very nearly right, because Alfarghani's mile was the Arabic mile of about 1970 meters, yielding a circumference within a percent of the truth. The French cardinal Pierre Dailly, compiling a survey of the world called the Image of the World in 1410, took the number and understood the mile as the Roman mile of 1480 meters. Columbus owned a printed copy of Dailly and annotated it densely, and that copy survives in Seville. Reading 56 2/3 Roman miles to the degree gives an Earth of about 30,000 kilometers, a quarter smaller than it is. Combine that with Marinus overlong Asia and his own arithmetic, and the Western Ocean shrinks to something a ship could cross. Columbus expected the Canaries to Japan to be 2,500 to 3,000 nautical miles, something under 6,000 kilometers, against a true distance more than 3 times as far. Had he believed Eratosthenes, at any stade anyone has ever proposed, the voyage he had in mind would have been impossible. Hultsch, who gave the short stade its canonical form, also wrote this. Generally, he said, we must refrain from calculating exact distances from indications of stades in Greek authors. A stadion can only be assumed to be the conventional expression of 240 steps. Greeks believed they had only one stadion as a unit of measurement. For them, it was the distance of 240 steps, but they had no idea with what degree of accuracy, or under what circumstances, that measure had been arrived at in any particular case. That verdict has gone unimproved for 140 years. A stadion was a real unit in the sense that everyone knew what it meant, and nobody could say how long it was. It was 600 feet, with the foot varying from city to city. It was 240 paces, and the pace varied from man to man, and from a cool morning to the middle of a hot afternoon. Eratosthenes saw that a shadow at one place and no shadow at another, on the same day, is a statement about the size of the world, and that it can be turned into a number if you know one distance on the ground. That much survives every attack on the details. The accuracy does not survive. Accuracy is a property of the chosen conversion factor rather than of the measurement. Multiply his answer by 157.5, and he is astonishing. At 185, he is out by a sixth. Measured against the track at Olympia, one of the handful of stades anyone has ever laid a tape along, the error is a fifth. The geometry is fixed, and the arithmetic is fixed. What floats is the length of a step, which depended on how long a man's legs were and how far he had already walked that day. 3 papers published in the last 8 years, by S.H. Cheglov, by Tupikova, and by Narduzzi, give 3 different answers for how long a stade was, and they do not agree on whether it was ever a matter of paces at all.